All right, here we are in video 3. So your task was to look at the graphs. What special circumstances are going on in these two graphs? I'm going to guess I'll put an X. In these two graphs that are preventing me from finding a point in my interval between my endpoints that will have an instantaneous rate of change that's equal to the average rate of change. And the answer is, well, there's something happening at these points. There's no smooth transition, right? There's no smooth, it's a very sharp turn. And so we have points of non-differentiability in the interval that we're talking about. So because of that, we're going to be prevented from finding a point in between the interval where that happens. And when I look at the last one, k of x, there's an actual break in the graph. There's a discontinuity. So that's going to prevent me from finding the point that I'm supposed to, that it'd be nice for us to find. I shouldn't say supposed to, because we're not supposed to, but we've noticed that in other examples, whenever I connect the endpoints and I draw the secant line, in between the endpoints that connect the secant line, we can find a point whose tangent line is the same slope as the secant line. But not in those. So what does the mean value theorem tell us? The mean value theorem tells us that if these two conditions are met, then we will definitely be guaranteed the existence of a point where the I rock equals the A rock. And this is what it says. My two conditions are this. I have to have a function that's continuous on the closed interval. So between the points, I have to have a closed interval. My graph cannot have any holes, cannot have any breaks, cannot have any asymptotes. It has to be continuous. And that was the problem with this graph. There was not discontinuity all the way at the endpoint. There was a discontinuity at the endpoint. I need there to be no discontinuities anywhere between the endpoints or even at the endpoints. And then the second thing, we need the function to be differentiable on the open interval. We need to be able to find the derivative at every point in between, which is what caused this graph to fail, is because I have non-differentiable points, and that prevents me from finding that magic x value. So this is saying, the mean value theorem is saying, if two things happen, if my function is continuous and if my function is differentiable, then there must exist an x value, which they're calling c, in the interval between a and b, strictly between a and b, that in which, or such that, the I rock, the derivative, is equal to the A rock, the slope of the tangent line. So the mean value theorem will guarantee that there's always going to be a point as long as, so there's two conditions, the function is continuous on the closed interval and the function is differentiable on the open interval between the endpoints. If those two conditions are met, we are guaranteed that there is a point where the I rock is equal to the A rock. If you think about it, and if I can go off the notes here a little bit, if you think about it, let's say that I'm driving from Kyle to Austin. And let's say that I am driving, we'll say I'm driving the speed limit for the most part, right? Because if you're like me, when traffic is light, I might tend to go a little bit faster. Or if I see a police car get on the interstate, I might go a little bit slower. But I can say that on average, I'm going the speed limit, right? I'm going 65 down I-35, the interstate. Am I always going 65? Well, no. I just said, like, sometimes I slow down if there's traffic, sometimes I speed up if there's no traffic. But overall, I'm going 65 miles per hour. So the mean value theorem says that if my average is 65, then it doesn't matter if I slow down or speed up. At some point in between my trip, I must have been going 65 miles an hour, right? Because if my average is 65, then when I went slower and then I went faster again, I had to cross that 65. Or if I went Faster, well, then I must have gotten back down and hit that average 65 miles an hour. So when you're driving, the odometer, right, is telling you the instantaneous rate of change. It's telling you your speed right at that moment. However, we can say that the average speed is 65 miles an hour because that's the speed limit. So we can then guarantee that if the speed limit is 65 miles an hour, unless you're going under the speed limit the whole way, there's going to be a point where you are definitely um, going that speed. Okay, getting off that. So there's a couple of things that we have to be aware of. We have to make sure that the function is continuous and differentiable on each given interval. Continuous on the closed interval, differentiable on the open interval. We have to know that the mean value theorem guarantees that the instantaneous rate of change is equal to the average rate of change somewhere in the interval. But remember, the mean value theorem is an existential theorem, an existence theorem. It tells me something occurs, it guarantees that something occurs, but it doesn't really tell me where it is, how to find it. It just says it's going to happen. And then finally, we're going to approach some mean value theorem problems that we're going to do very similar to the intermediate value theorem, which is we got to check and state the conditions. We have to use the endpoints and then state the conclusion of what the theorem says. And so before we get too far, we have a couple of problems here on the bottom part of this page in example 2. So we're asked to read the information and determine which existence theorem is appropriate. Am I going to use the intermediate value theorem, or am I going to use the mean value theorem? And then verify the conditions to see if that appropriate theorem can be applied. We don't need to finish and apply the theorem. We just need to see which one are we going to use, and do we have the conditions in order to do so. So just a quick reminder. The intermediate value theorem said that if I have 2 points, 2 x values, right? And if I have a function, then I know the y values of the endpoints. So the question, or the big idea behind the intermediate value theorem is there has to exist, if my function is continuous, and that's the big if with the intermediate value theorem, if my function is continuous, then any y value that's in between, now it doesn't even have to be halfway in between, just somewhere in between my endpoint y values are going to produce, there's going to be an x value, maybe I should call that C. There's going to be an x value in between A and B that will produce that y value. So as long as you choose a y value that's in between, I'm going to call this L. As long as you choose a y value that's in between the y values of the endpoints, then and as long as my function is continuous, then I'm going to be guaranteed that there's an x value in between my A and B values, x values, that produce whose y value is that number. Okay. So when I come back over here, how do I know whether it's the intermediate value theorem or the mean value theorem? And if you don't mind, I'm going to go ahead and write out the whole word, not just IVT and MVT. So here's the first setup. There's a function that's continuous for all values of x. Selected values of x are given in the table. Is there a time c, where c is between 1 and 7, such that f of c equals -2? Give a reason for your answer. So this is an intermediate value theorem problem. Why? Because, maybe I should have abbreviated, because it's asking about a function value, and the information given to me is about that function. So it's telling me, is there an input, or an x, which they're calling c, is there an input such that f of the input equals my output of -2? So it's all about the function that's given in the box. Do we have the conditions? Yes. We have the conditions because all we need is for f to be continuous on the interval. On the interval between 1 and 7. How do I know it's continuous? Oh, because they told me f is continuous for all x values. So as long as I know that, then we're good. Let's see. When I look at the second part, is there a time between 1 and 7 such that f prime of r is equal to negative 2? Well, this is about the mean value theorem. And I know it's about the mean value theorem because what they're asking me about is not about the function that's given, but about the derivative or the rate of change of the function that's given. And that means we're using the mean value theorem. So do you see the difference? One of them is asking about f of x or f of c, which is the function that whose information we're given. The other one's asking about f prime of r, and that would be the derivative or the rate of change of the function that we're given. Now, the question is, can I use it? So the answer over here was intermediate value theorem, f is continuous, that's what I needed. But when I look at this, for the mean value theorem, we need f to be continuous on the closed interval, but we also need f to be differentiable on the open interval. And based off of the information that we're given, only one of those is guaranteed. According to what's written, the only thing we know is that the function is continuous, so this checks out. But I don't know if it's differentiable, so therefore that doesn't check out. And if I don't have my two conditions, then I can't do the mean value theorem. So right now, we're not actually doing anything with it. We're just trying to figure out which of the two big theorems that we've talked about does this particular problem question apply to. All right, last one. For t's that are greater than or equal to 0, the velocity of the particle moving along a straight line can be modeled by the differentiable function v, and selected values of v of t are given in the table. Problem A, must there be a time k, where k is between 2 and 11, such that a of k is equal to negative 1? Give a reason for your answer. Okay, so we're going to ask ourselves, what are they concerned about? What are they asking about? Well, they're asking about a of k. And by a of k, they mean the acceleration. Is that the information that we're given here? No, this is the information about velocity, right? These are all v values. So how is acceleration related to velocity? Acceleration is a derivative of velocity. So therefore, it's the rate of change of velocity. So therefore, this is a mean value theorem type of problem. And so now we're going to check, are the two conditions met? I need f to be continuous on the closed interval, and the closed interval here would be 2 to 11. And I need f to be differentiable on the open interval, and the open interval would be from 2 to 11 as well. By the way, over here I should have put parentheses around the 1 and the 7 because it's an open interval between 1 and 7. All right, let's check. How do I know if this is true? Well, kind of easily, because they tell me the velocity of the particle can be modeled by the differentiable function v. If it's differentiable, then this checks out. But if it's differentiable, it has to be continuous. I can't find the derivative if there's a hole. So if the derivative exists, there's not a hole. I can't find the derivative if there's an asymptote, vertical asymptote. So if it's differentiable, that means I can find the derivative. There is no vertical asymptote. So it has to be continuous on that interval. So therefore, for letter A on this last problem, we can use the mean value theorem because the condition is met, and we are guaranteed that there must be a time k in between that interval such that a of k is equal to negative 1. That's the mean value theorem. We'll come back, we'll do some more problems, and we'll kind of wrap it up that way.